Welcome to Center of Math's Advanced Knowledge Problem of the Week. For this week's problem, we're given that p is between 1 and is less than infinity, so it's not infinity, that fn, f are in LP, and that fn goes to f almost everywhere. We're going to prove that the LP norm of fn minus f goes to 0 if and only if the norm of fn goes to the norm of f in this scenario. So first direction, let's assume fn minus f, the norm of that goes to 0. So for the first direction, we're just going to make use of the triangle inequality. So by the triangle inequality, we can kind of reverse it. So you have fn is less than or equal to fn minus f plus f, or with everything having norms. From there, we get this. We can get this upper bound on fn minus f. This is essentially just the triangle inequality kind of turned around. And so since LP satisfies the triangle inequality, we'll have this inequality. And the right side goes to 0. And so these terms must approach each other. So and so we get that as n goes to infinity, f of n and LP norm of f of n goes to the LP norm of f. And so that's one direction. For the other direction, we're going to find a sequence of positive functions and use Fatot's lemma. So first, quick inequality. So note fn minus f note the absolute value of fn minus f to the p is less than or equal to 2 times max fn minus f. This is just fn minus, this is all at some value, at some x point in our space. So this is less than 2 times max fn comma f. So clearly, yeah. So yeah, fn minus f to the p less than or equal to 2 times max absolute value of fn comma absolute value of f. And this is less than or equal to 2 to the p times absolute value of fn to the p plus absolute value of f to the p. These are some pretty simple bounds. It's just maximum of 2 elements is greater than either element. And then the maximum is less than or equal to that. The maximum of 2 elements is less than or equal to the sum of those elements. These are relatively simple bounds. And for this bound, we can find a sequence of functions that's always going to be positive. So we're going to consider 2 to the p times fn to the p plus absolute value of f to the p, the thing on the right, minus the thing on the left. By our inequality, this is always going to be greater than or equal to 0. And now we're going to apply Fatot's lemma. So that's going to give us a new equation. To our sequence of functions here, this is always positive, so we can apply Fatot's lemma. And so we have the lim inf, it's going to be less than or equal to the lim inf on the outside. And so once we carry these limits, so the limit fn approaches f pointwise, so the lim inf of that is just f. And since these approach a concrete limit, we can kind of pull it out. And what we're going to be left with, and we're going to see that the supremum of fn minus f, the lim sup, is going to go to 0. So this term on the left side, each of these terms is either going to go 0 or some concrete number, and the terms on the right Some of them are going to drop out, and we're going to be left with a lim sup. So writing this out, so now we take a few limits. So this lim inf. So on the left side, we're going to note that since fn goes to f pointwise, this lim inf of f of n just becomes f. Again, we're just using this pointwise convergence. This becomes f of n's just become f. So this is going to drop out. This term is going to drop out. And we're left with terms in terms of f on the left side. On the right side, so the lim inf is on the outside integral. So for this, we're going to note that on the left side, the left two terms on the left side, they converge to a definite value. So this is where we use that f of n in the LP norm converges to f. This allows us to put the lim inf on the integral of f of n and say, turn that just into f. So that's where we get the integral of f here. Integral of f does not depend on n, so that stays the same. And last term on the right, we pull the lim inf inside the minus, it becomes a lim sup. And so now we have something with less n's involved. And now we're going to do some cancellation. So these two terms on the left are also on the right, so we cancel them. This term becomes 0, and we're left with the lim sup of f of n minus f to the p is less than or equal to 0, but the lim sup of this has to be positive, so it must be equal to 0. And so we have the lim sup is in fact equal to 0. And so the limit of this, the LP norm, in fact, of fn minus f, is just this term to the 1 over p, must in fact approach 0. And that proves our theorem. Thanks for watching. Please check us out on Facebook and Twitter. And please check out our blog on centerofmath.org. Thank you.